Our recording has been started right now. Okay, so this is the continuation of yesterday's lesson, and we just examined uh, the odds ratio for the uh, uh, logistic regression. And this was the last point that we have examined, and this was um, the formula for odds ratio, and how. So this is how we predicted some models, uh, 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 some outcomes based on um, logistic regression. There was a binary uh, um, problem, which is yes, no. That we had a data set of uh, uh, bank's customers. So then it was time since last purchase, and has churned or not churned. So we just examine the churn data, and this churn is just a binary um, problem. 0 is not churned, and 1 is churned. So this is how the model predicted the values, and these are the likelihood of churning. So this model is predicting. But we wanted just to make it round up and get only 0 and 1. And this is how we got those numbers. And then we visualize this uh, outcome of this prediction. We came to the mm, odds ratio, define the odds ratio. What's odds ratio? Then now one more thing which remains here. That's actually the interesting thing is here. That's the confusion matrix. Confusion matrix is one of the major um, um, actually uh, matrices or KPIs for not only for regression models but also for other models as well that we will be later on studying. So this is one of the major scores that you have to pay attention and understand the efficiency of your model that you are developing. So just let's code this and understand how it will look like. For example, if uh, mm, from the above model, we want to know how much actually churned, yeah? So uh, it will be data, and it will be as churned, yeah? So this is actually the list of actual responses, yeah? So this is the list of actual responses. Um, Almost 400 rows in this data set, and this is only the actual responses, so without prediction. So we just want to point out that separately. And then now let's see the predicted responses. Yeah. So the predicted responses um, is actually the prediction data that we had, uh, but has changed, but not the prediction data, not this one, uh, not the prediction data, this one, round off one. So we don't need the likelihoods here. We just need the round off one. So the whole thing which has to be 0 or 1. If you just get the prediction data, so it will give you this percentage of likelihood. But we want to just 0 and 1, so to examine that. So then the response will be the prediction data has changed only the round off one of it. Or maybe just what is the prediction data here? I just want to know the prediction data here. Okay, explanatory data data set. Okay, no, that's not the prediction data. This is the prediction. This is a model recency. Okay, has changed since last purchase. Data bank data. So this is the model recency. This is actually the model. Yeah. So this is the model that we developed. So just the prediction data would be this model dot predict. Yeah. So it will be this model and yeah, this model dot predict of explanatory data. Just let's assume something else. Instead of putting that, let's put the model recency, the whole model. So has churned time since last purchase, date of it. Yeah, that's the model, the whole model. We will be just putting the whole model here. Predicted response is so instead of this data frame that we have developed later on, we will be just put the model recency dot predict. It's the same thing. It's the same thing. And then we will just one more thing that we have to understand, that's the outcomes. So outcomes of this data will be actually the data frame, pd.data frame of actual responses and predicted responses. Yeah. So we want to create a data frame of what? Of actual responses and predicted responses. We just want to have a look at it. Yes. So how it will look like. Just run this. What is the problem? This is the problem. Okay, so this is the data set actually. If you have a look at the data set, look at this data set. So this is the actual rating, the actual churning rate, and this is the predicted one. See, look at this. This is 1, but the model predicted that it's 0. See, one of them that is distinct. This is why we want to develop such a model and understand. Now let's do something else. For example, to have a proper understanding, let's counts dot value counts. Look at that, for example. This is actual and this is predicted. So for actual, which is 0, 141 is also predicted 0. But actual is 1. For that, the prediction model only 89 has been predicted correctly, and 111 is predicted not correctly. And here, the actual model is 0. The model predicted 59 1. Did you understand what I have done here?
Yeah.
Perfect. So this is how we want to try to understand if the model predicted properly or not. Now, this is actually confusion matrix. Nothing else, nothing complicated. That's confusion matrix. It will be this model recency that we have, this model that we have here. This model dot pred table, the prediction table of this model, and in this confusion matrix, and this is it, 141 59, 111 89. This is the very interesting mathematical calculation side, and this is the confusion matrix. 141 predicted true, yeah. 59 predicted, which should be 0, 59 predicted false. So, see, it should be 0, Look, this is now perfect. So 141 predicted correctly, 59 incorrectly. See, in the second category, 111 predicted correctly, 89 incorrectly. See, for both classifications, for actual ones. So this is a type of confusion matrix that we have developed here, and now this is the the understanding of confusion matrix. So
Sir, sorry, in the second one, which is 111 is incorrect and 89 is correct.
yeah, 89 is correct, and yeah, so this is like matrix. This one, this one, this one, this one. You got you got it.
Yeah, it's okay.
Correct and correct, yeah. Correct and correct. So it's like this. Yeah, exactly. So this one is incorrect one, and this one is correct one. This is like matrix type. So this is correct, this is correct. This is incorrect, this is incorrect. And let's do something else. If it works, that you will be understanding it um, perfectly if it works. If not, so that's okay. Now you understand what's from mm, from that model. We can dot graphics import mosaic. That's perfect. Mosaic plot import and mosaic, not actuals. Maybe we can do that. Yeah, that's good. That's very perfect. We can do that as well. And instead of instead of this, you can put just simple confusion matrix as well. You will see. Yeah. So this is called now a confusion matrix just to understand. So this is the actual responses and this is the predicted ones. See? So this is the actual response, this is the X side, and this is the predicted one. So for the actual response, which is 0, yeah. So this is the actual response, which is 0. 141 is 0. So this is correct. 0 0. See, this is actual response. This is prediction. This is 0 0. That's correct. For the response, which should be 0, we have 59. A small portion is 0 1 is incorrect. This portion is incorrect. See, this is correct and this portion is incorrect. For the second category, which is category number 1, 111 is incorrect. This much is incorrect. See, this much is incorrect. 111 is incorrect. 89 is correct. Only this portion is correct. So we have this portion correct and we have this portion correct. Now, from confusion matrix, you will see and you will understand that in 0 category, which is not uh, churned, the prediction of model is much more accurate, yeah? But for the second category, the prediction of model is less correct. You got how the confusion matrix will give you the understanding of this. So this 141, which is correct in the category, that's called true negative. Why true negative? Because 0 not churn, yeah? So that's true negatives. So 0, this one is true negative, yeah? So this is why this is negative, this is positive, yeah? So 0 is negative, it means not churned. 1 is positive, churned, that's positive, yeah? Actually, from the logical point of view, that's totally different thing from bank point of view. But this is from mathematical point of view, from 0 and 1 point of view. From bank point of view, who has churned, so that's bad for the company, for the bank, yeah. So because they churned, they went away, they lose the customer. But just don't go to that philosophical understanding of it, but just assume that this is how it will work. Now, coming to this is called true negatives. So 141 is actually true negative, 0, 0. And this is false negative, yeah? So this is negative and this is false negative. And another is true positive, which is, this is true positive. And this is false positive. So this is how it works. This is called confusion matrix. Now, what is the accuracy? Accuracy is the proportion of, I will just give you the, I will try to get to give it to you. This is the, okay. Now, from confusion matrix, you can define the accuracy of a model. Accuracy of a model is very, very simple. So true negatives plus true positives divided by true negatives plus false negatives plus false positives plus true positives. You got, so how, so all the true ones, you will get all the true ones. This is the true one and this is the true one. This true one plus this true one divided by sum of all other ones. So this is called the accuracy of our model. And this accuracy is one of the major points in this model. So tell me from this confusion matrix, what is the true negatives? Let's define the true negatives from this confusion matrix. This confusion matrix. Confusion matrix will be having elements, yeah? So this one, this confusion matrix. So what is true negatives?
That is 0, 0.
Perfect. 0, 0 is true negatives. And what is the false negative?
0, 1, 1, 0.
Exactly. False negative is false negative. How much? What is the false negative? Look at this. What's the false negative?
0, 1.
1, 0.
1, 0. Here you can find it very well. So this is false. This is true negative. This is false negative. Yeah. So this is matrix. Yeah. We want to go through this area. So this is true negative. This is 0, 0. This is 0, 0. If you want to go to the false negative, then it will be 1. This column 0, column 1, column 1, row 0. So it will be confusion matrix, column 1, row 0 still, yeah? So similar, you got the I will not just false positive and true positive. So false positive will be 0, 1, and true positive will be 1, 1. So the same thing for this matrix. So this is the false positive, and this is the true positive. So false positive is row, second row, column 0. So second row will be 1. Not this is 0. This is 1. Column will be 0. So 1, 0. False positive, false negative, false negative, yeah. Or 0, 0, 0. Sorry. Okay, that's good. So this is 0, 0. That should be true positive. 1, 1. It is false negative 1, 0. It will be 0, 1. That's good. This is matrix. Now let's try to define the accuracy. How to, based on this formula, we will define the accuracy, and we will do that Tn plus Tp, which we have Tn plus Tp, and then divided by Tn plus plus Tp plus Fn plus Fp. Okay, run this one. No, first we have to run this one. Then we have to run this one. This is the accuracy of our model. What does it mean?
Oh, about 57%.
Exactly, 57, almost 0.5%. The model is accurate overall in general. So this is the accuracy of our regression model that we have developed. This is how the accuracy is defined for this model. Similarly, another function, which is another measure for the model performance, is called sensitivity. Sensitivity is also one of the major things that you have to all the time consider for the models. And what is sensitivity? Sensitivity is the proportion of the true positives. So true positives are also very important. Models in general, for example, one of the things, for example, if someone tells you, okay, develop such a model for us that at least the accuracy of the model should be around 85%. Okay, you have developed that model, and that's perfect. You developed that model, but all the time you have to check for not only for the accuracy of the model, which is 85%. You have to check the sensitivity as well. What is the sensitivity? Sometimes models, for example, look at these ones. Now this is the true negatives, yeah, and this is the true positives, yeah. But sometimes models are very good in one category, and this is why the accuracy of models gets increased, yeah. So for example, this is very to this point it's accurate in this model, while in this model it's to this point false. So in this category, you got the point that then the model actually, the overall percentage of accuracy will be somehow satisfactory to you, but then you have to understand the sensitivity as well, that you have to understand how much true positives were there actually. So now this is the true positive, and sensitivity of our model is sensitivity will be actually the TP divided by false negative plus, and we will check that sensitivity. That will be 44%. See, this is somehow modulus. It shows the sensitivity of the model, this percentage, true positives. So this is actually this much the model is predicting true positive values. One more thing for the models, which is for these models that's very playing a key role. Another function that you have to understand. So now we just find the true positives. Yeah, if you want to know the true negatives, then that's called another measure for the models, for such models. That's called a specificity. This is the proportion of true negatives. So this was the true positives, and this is the proportion of true negatives. And you have to check also this for the models whenever you are developing such models, and that will be this will be 70% almost. So for the true negatives, so this model is actually having a higher prediction. See, 70%, this predicts true negatives or correct, and that's it. You can see here, look, this is 70% almost. This is true negatives, yeah. So 0, 0 is true negatives, and the model predicts very well the true negatives. While this is the true positives, yeah. Model is not good in true positives. See, in this square, which is 1, 1, the model is actually 44% accurate, and here it's 70% accurate. So this is, see, 44%. This is 44%, and this is 70%. This is how these different specificity in different uh, uh, things. These are the names of these different. Uh,
Whether
just
in conclusion, is the model not good?
you cannot define that which the model is not good or not. This is very difficult question all the time whenever you're developing. We cannot define that, but these are the things that you have to understand how the model works. You know how the model works. This model works if you are predicting true positives, true negatives. Yeah, it works very well. It means it predicts the zero category. That it predicts one category very well, another category not very well. So overall, the accuracy of the model is 57%. This much accuracy is not acceptable. Never. It's going to be accepted as a successful model to predict something. Because at least when models are considered to be successful, at least the accuracy should be more than 70%. So 75%. If it's more than 75%, then they will think about it that okay, this model works. Now we have to find another ways to enhance it, to to enhance a model. It's called, from modeling point of view, hyperparameter tuning. So that's a specific technical term, hyperparameter tuning. So then you will think about that okay, let's fine tune the model, see which is what is lacking in the model, and bring that good thing in the model, or maybe new features that we will predict. But if the model accuracy is just below 75% at this level, then you will not even think about the hyperparameter tuning. So it's not a successful model actually. So this is how you will define with a model how to proceed or not proceed. And you will see in our later on exercises that why this model is not successful. So we will discuss that later on. But this is just not about the model accuracy. This is about the understanding of confusion matrix, understanding of the accuracy of the models, sensitivity of the models, and specificity of the models. These are all the terms that you have to understand, and you have to be very aware of it, how it will works, and all these things, that how they will work. So this is actually the specifics about the model, about the logistic regression models that we had developed. Now let me go to another things. For example, maybe this is called the performance of the logistic models that we just did. Let's proceed with some. There are two other topics remained in this portion. One is the intermediate regression, that we can proceed with multiple linear regressions and multiple logistic regressions. That's also we can do. And another thing is also hypothesis testing. So both of them are important, but I just wanted to decide which one we will go. Either we have to go with the hypothesis testing, or we have to go with the multiple linear regressions. It depends that later on, because if we decide to proceed with one of them, then later on we will um, we have to understand, for example, that in modeling that we have to, we should. So let's proceed with the multiple linear regression. I think that you will understand how multiple linear regressions can work and what's actually the multiple linear regression. Now, we had a data set yesterday that we have developed, and that data set was from the fishes, yeah, if you remember. I think let's call that data set, see if that's already there. It is not there. Okay, let me go back and see where we call the fishes. Okay, this is the fish data set. See it. We have a species, mass ground, and length of that data set. Yeah. So we have length, we have height, but we don't have. So this is the fishes. I think this is not the sufficient one. We have to find the sufficient one. I will upload the new data set and copy the path here. And fishes will be the um, okay. And now again, yeah, we need a new column here actually. So this is why I wanted to find maybe that's not there. But if we have a new column, for example, in this data set, and that's actually the uh, for the fish data set, for example, new column, which if we have length right now, length of that, then mass of that, and then species type. If we have another column, which could be the height of that data set. So if you want to visualize that height and length together, then I think I'm just trying to find this data set for myself as well, but I cannot find it because this data set is still. We should work in Kaggle sometimes because in Kaggle there are data sets are there. So you can find it in Kaggle if you have access to it. And let me if you found it there in Kaggle.
Sir, we may use any other data set, like, for example, plant growth data classification that has many
Yeah,
parameters.
that iris, you mean, data set. Yeah, we can use that, but still, why I'm just saying this data set, because this data set we did it yesterday, so we predicted something yesterday, and this is the continuation of how uh, we used yesterday. This is why I'm thinking that, because whenever you're using something new, then uh, you have to go through it again. Yeah. So let me see if this works. If not, then we will be proceeding with something else. We will be thinking about totally different one. But this I think works. So this is the mass, species, mass, length, and height. So this is the new data set that we want to have a look at it, and because we want to have previously we had only the length of the species. Yeah. Now we have the height of it and the mass of it. So there is another numeric column. Whenever you are having another explanatory numeric column, so this is multiple linear regression. So you see, this is how it will work. Now let's visualize this one and see how it will work. For example, if you want to visualize this, so scatter plot, and then if we says okay, the x would be the length of it. It will be the length, and the y will be the weight of it, and the hues will be the uh, uh, not species but the mass. Copy, and that would be the mass of it. Mhm. And the data will be the fishes. And close it, and what happened to that?
Instead of weight, we have to use height.
Not height, exactly. There is no weight. There's height. And still we have a problem because this is the problem. This is a type of scatter plot which gives us the length, the height, and the mass. Mass is actually in this way. See, this is the gram of mass. So this is the length in centimeters. This is the height in centimeters. So see, this is a type of scatter plot from this, and these numbers, dark numbers. This is actually the heavyweight fishes. Uh, Lower numbers, these are the lightweight fishes. See, so one more thing, which how you can interpret this data, how you think about it.
As length and height of the fish is increasing, the mass is increased.
Brilliant. This is the proper interpretation of this scatter plot. Now let's model something for this. Model what? Model actually the the mass versus, let's call it both. Both what? Both both height and length. If you remember, we used the mass column, if you remember it, yeah. And instead of only length of it, yeah, If you want to do several regression models, how you can do that? Now, in several regression linear models, this is the mass. This is the target variable. See? Or another name of this variable was what? Someone tell me.
Length of the fish.
No, length is okay. Yeah, that we will get that. Length. We just did mass and count through the length. Yeah. So this was the model that we have developed here. We define the mass and then we define the length instead of the length. So length was explanatory value and mass was response value or the target value. Right now, so we predicted. This was our predictions. We wanted to predict the weight of the fishes based on the length. So we provided some length to the model, and that length actually predicted weight of that specific fishes. Now we want to predict the weight of the model, not only based on the length of it, but based on the length plus height of
And
it.
height, yeah.
So this is multiple linear regression, and we want to do this. And what will be the data? The data will be the fishes, and this model we will be fitting it, and you want to develop it. What is the problem again? Height is not defined. Height is not defined. Is this not defined? Copy.
استاد یک بارم قوسار سعی کنید فکر کنم یک دانه اضافه تر بس داشته.
Yeah, after
No, that's not fit.
that's it, okay.
That's the count. The other things are accurate, but the point is that it says that the height is not correct, which is there already. Maybe one more thing. I will just want to check that the columns here, the exact name of columns sometimes. So this is the height. One more thing maybe here. The problem. I understand now what's the problem. Because let's try this one. Maybe computer is not understanding it properly. Who knows? Yeah. Because there is a space between there. See. So and this one. So mass gram is equal length plus height plus that would be actually the proper one. but still it doesn't understand it. Maybe this type. You have to again. I just changed the name because these spaces are making problems here. It was the problem with the spaces between these ones. I think now it's resolved and we will see what is there. So this data set had spaces between the columns here, these spaces, and these brackets here. So I just rename the column name, and when I rename the column names, so it's now working. So we will see now how this model worked. This Yes, this model, this regression model, see this params. What are the parameters of this model? This is the intercept, and this is the length, and this is the height. So we have previously we have only one um, parameter. Now we have two of them because we examined that with the length and with the height together. So this is how we did it. Now let's do something else and then understand, for example, that do some predictions and see if this model is working for both of them. Does the prediction is working or not? Uh, we should iterate some new arrays and we should from iterations, we should import the product, which is you will later on see why it's important. We will be having length in centimeters, and we should generate something here. We'll just assume that let's generate an array of, for example, 5 to 61, 60, which we should define it 61, and then also let's generate something height of, for example, in centimeters. Again, in P range, in between NP range, for example, between 2 to 20 to 20. This is 2 to 20 actually. The steps would be 2 for each one, and now we need the P. It will be the product of. This is the product of two arrays. It will be the length centimeter and the height centimeter. So these will be the products of these two ones. This is how you can do that. Now, just the explanatory data will be actually the PD dot data frame. Again, we want to put it in a data frame of what? Of P, and the columns will be actually the length in centimeters and the height in centimeters. So length in centimeters, and then height in centimeters. So if we run this one, so this is a data frame. The length and the height is there. With different one. See, different. For example, different length, or different length, different height. So we had these two different. This is one array we generated. This first array. Then we generated second array. Then we generated a P. P is type of product. So productize these two arrays together. Yeah. Now we generated a data frame. This type, this type. So this is just a random data frame that we have generated. A length and a height. And we don't have the mass here. See? We don't have the mass here. So we have a height and a length, and we don't have the mass here. Now, based on these two numbers, previously we had only length, and based on length, we predicted some mass. Now we want to predict, based on two of them, the mass of the fishes. Now, let's do that, how the prediction data will work. Prediction data will be working off this explanatory data. Yeah, just make it a new column there. Assign there. Mass will be mass will be model mass versus both. This model that we have developed, this one, this model. Put the prediction of explanatory data. This is the explanatory data we did. So this is the prediction data. So just develop that here in this length to create a new column called mass G, for example, and predict the model input, the outputs for each of them. We ran this model, and this model worked properly. Is it working? It is working actually. It is working. It is working actually. That's good. Now, instead of this, let's do something else then. Prediction data will be the model mass versus both of explanatory data.
Is it the capital letter? That's the problem.
That's the problem.
The height. You also
You think-
changed the data. The
No, that's okay.
centimeter was not there, I think.
No, this is. I'm just taking this one. But no, the point is something is missing with my the way that I'm working here. Um. There is the problem, I think, in for H and Y. So these are okay. These are.
Sir, your second length. No, the third one, yes, that one should be HT.
Yeah, G is not needed there, I think. The length.
Yeah, that's okay, but this is how it says wrapper is, this object is not wrappable. So I just want to know, this is why. No, this error, we can get the explanation of type error. What is the problem with this error? So this ran properly. Okay, that's good. So it means this ran properly. This ran properly. Am I right? That's good. Now we should run this one. Again, it says explanatory data is
Sir,
not
you
running.
didn't use the dot predict after the model. Model mass versus bot dot predict, I think.
Dot predict model mass versus boot dot predict. Should be explanatory data, yeah? So just let me check the explanatory data. This is the explanatory data. Yeah, this is the length and this is the height. That's okay. Now prediction data will be model mass. Yeah, it will be dot predict and explanatory data. So just let's do that. Again, it says it's not working here. Dot predict and then using the predictory data. So you will see what's the problem here. Again with the length and height, what is the problem with the length and height? So okay, we will check this one. One more thing that we didn't import all the time, that's the SMF model. The SMF model all the time. Okay. So what is the difference between what we are doing? Okay. This is the length, we generated this length. This is the height we generated. Okay. This is the explanatory data. We generated the explanatory data. Now the explanatory, the columns, these columns that we have generated, it should be renamed back like the original data set. We forget that one. So this data frame that we have generated, this length centimeter, yeah, this height centimeter, this is a new data frame that we have generated here, yeah, as an assumption. After the generation of that data frame, it has to be renamed back to the main data set, because model doesn't understand this length centimeter, model understands only this length, which is here. And it was generated based on that model. So this is why, again, with the yeah. So the way is 100% correct way. So this is how our model predicts now.
Yeah, it was a capital letter.
Yeah, it was a capital letter and without centimeters. No, the point is that we have generated a new explanatory data framework. Yeah. Whenever you are generating a new one, a new something new one, then these names, for example, which we have developed, yeah. So these ones, or these ones, these length or these height, it should be 100% the same as the main original data set. Otherwise, the main original data set, for example, we have developed such a data set here, which is length centimeter and height centimeter, while the main original data set has only length with capital L, in height with capital H, which we change it here. I forget that we changed we changed the column names here. See, we just put the length, height, these ones. This is so the way is the correct way that we did it. So we develop a model, then based on the model we develop a we generated some new numbers, and based on some new numbers, so new numbers of what? Of length and height. Then we want to predict the mass of that specific fish. We have so it's also the same thing, yeah? Yeah, it's the same thing. Just remove this one. And maybe this one is required. Yeah, so this is a new data set, a new data frame. So we put everything together. So length, height, and then the mass. So look at the mass, which is sometimes negative, and why it's negative sometimes. For example, if you see that the different thing. Now let's plot this. This one, and see what we can understand from this prediction data. So we will be plotting SNS scatter plot. Actually, this is the exact what the hue will be the mass exactly. This will be for the data from the fishes. Again, mass GPI. Again, problem with the mass. I think it's capital M, yeah. Fishes dot odds. Yeah, it's capital M. It's capital M. This is the scatter plot for the original data that we had, yeah. And now we want to develop a scatter plot for the another thing that we have developed recently. That is the SNS scatter plot. This is for the prediction data. So this will be for the prediction data. And let's change the marker to is squares that we have to differentiate. Is it good or not? So just, and also just make the legend false and PLT dot show and have a look at this. So this is now combination of our prediction model and our actual model looks like. So these are the squares one or the predicted ones, and the dotted ones are actually the ones with the actual values. So these are some minus value as well. So those ones are actually the thing that we have to understand, that because these are not the valid combinations. So it means the not valid combinations. What does it mean? These minus ones. It's the not valid combination. It means such a fish with a mass with a length of 5 and a height of 2 actually is, if you are going through a regression model analysis. So this regression model analysis actually will not predict such a from mathematical point of view, it will predict something because this is a linear regression model. Yeah. So based on the linearity and based on the um, uh, the characteristics which this model has, it will predict that. But you will understand that this is not a valid number because mass cannot be the negative one. So that would not be a proper understanding of how the model will works. But still, the model predicts something because for the model, it doesn't make any sense. The model is actually working, yeah. So the same way that it's just predicting, because for model, it doesn't understand the context of how you will think about it. It just seeks the relationship between variables. So if that relationship is working, model will predict something for you. If that relationship is not working, so model will not uh, uh, generate something for you. But you have to understand at the end that all the time, those predictions, as we previously got to know that from different points of accuracy, sensitivity, and all those things, those are not valid things. So I hope you got to understand it and you understand it how it will work. So this is why we studied all these other matrices here. These specificity, sensitivity, accuracy of the models that you have to try and understand it. For the model, it's just predicting something. And the aim of this showing this model for you was actually that you can have multiple linear regressions. The only difference between multiple linear regressions are that you will just put a plus point here. It means predict the mass based on the length plus height. So just do the length plus height and then predict the mass for me. Or maybe length divided by height, or maybe length just multiplied by height. So you can define this feature by yourself and then predict this linear model and then understand the outcomes of that. So this is how the multiple linear regression model works all the time, but it doesn't mean that all the time these numbers are accurate ones. These are just mathematical explanations based on the relationship which exists in the data. This is now the human understanding how to deal with it. So similarly, we can understand something else. For example, the logistic regression model. Previously, we had a bank data. If you remember, we had a bank data, and we used only, for example, the has-churned based on this time since last purchase. Yeah. So this was our model that we used. Now let's and this was the logistic regression. The logistic regression is actually the categorical. If we have categorical values instead of numerical values. So this was one of the things. Now let's see if we include both of these columns into has churned or not churned column. So this is also the same thing that we did previously, and so these are different functions that you can use here. For example, for these different things. So the same thing that we used previously. So if you remember, we had a confusion matrix previously called. In that confusion matrix, if it's still it's there. Confusion matrix, if it's still there. If you yeah, that's still there. That's good. This was the confusion matrix, and for the true positives and true negatives. So now, tell me how do you think that logistic regression, multiple logistic regression will work. What is your understanding how it will work? It will just the time since last purchase and the time since first purchase. You can do the same thing with it. So you can do, for example, you can have different logical variations. I'll just bring you the main formulas here for you, that you will just use those main formulas for you. For example, you can have a logit function and you have response variable with you can have logit function. This is the logical, yeah, and you can have response variable instead of one explanatory variable, yeah. This was how we used data something to data, yeah. So this is the general understanding of how you will use it, and then the fit. This is the one type of logistic regression that we use. This is simple logistic regression. Now, another type of logistic regression is actually the response variable. We want to examine it based off the explanatory variable plus another explanatory variable. So that would be two of them. So as we did for the linear regression as well, the same thing. The data will be data set, and that will be the fitting of the model in that fit. It won't run. It won't run because there is nothing here. And similarly, we can have another one. Instead of plus one, we can have the product of one of these ones. So multiplying the same two explanatory variable. So explanatory variable 1 and explanatory variable 2. So this is the main formula for both logistic regression, multiple logistic regressions. The same which we have done for the other ones. The true positives, true negatives will be the same. There will be nothing changes in those ones, and that will be the same thing. Now let's come and understand a new topic of this. It will be almost the end of the topics for the logistic regressions and for the linear regressions, that we have to understand the density functions, some density functions. So we will be understanding the density functions, and we will be trying to explain to you, for example, what is the density functions. Different things. So just let's start with the Gaussian probability density function that's called PDF. PDF is actually a mathematical function that describes the likelihood of a continuous random variable taking a specific value. It's a bit difficult for the start, but you will learn it whenever you're doing these modeling, and whenever the next models, when you're going to do some machine learning models development, then you will be more familiar with it and understanding it properly. This is the formula for the Gaussian. This formula is a bit Gaussian PDF, they'll call it. What's Gaussian PDF? So just let me write it here for you. It will be Gaussian density function. So this is how you will be understanding it, and this formula is a bit difficult, but still you can understand it. Now let's understand it properly within an example, and I want that you will understand it properly. Just assume that we have a height of people. So that's an example. So this is the formula. For the formula, if you want to know what everything means, so I will just put another thing for you, another explanation of this formula for you. Then here you will be understanding properly what's the exact value of everything of this. This doesn't mean. So this is X is actually a random variable. Mu is the mean of the distribution. The mean, this is the mean of distribution here. See, this is the very formula. Mathematically solving this formula will take a lot of time for you, but from Python point of view, it will be very interesting for you to just solve this one, and it will be very interesting for you. Let me give you an example. For example, we want to predict, just assume, for example, height of a group of people. For example, the mean value, for example, height of group of people. This mean is actually, it's equal to 170 centimeters, for example, the average value. And the standard deviation is actually, standard deviation is actually 10 centimeters. So just assume that you have these ones. And then after that, this based on the formula that we are having right now, Abba, let's understand the probability density for a height of a person, which is actually the height of a person, which is actually 100 x 180 centimeters. So how much is the probability density function? This is the probability density function. This is how it will be the probability of this height with a curve. This curve is mu. Now we want to understand the probability of a guy with a 180 centimeter, and let's solve this step by step. And then at the end, if you put all this in the formula, this will be the this will be 180 1 by, for example, now x will be 180, mu, which is the mean of people, that will be 170 centimeters, and then standard deviation, this one would be 10 because we have that. Then the pi, everyone understands that's the pi value, and the e value, everyone is also understand that's the e value. So I hope that you understand how much is the Euler value. Who can tell me how much is the Euler value? That's 2.7, and pi is 3.14. So these are the values that you can then Google it and understand what are those values. So if you put all these things that we have right now, we have pi, we have standard deviation, we have mean, we want to find the x, which is the 180 centimeters. If you solve all these things and put all in this formula, you will receive a response of almost 0.02, actually, I think, like that. And what does it mean? It means the probability density for a height of 180 centimeters is actually approximately 0.02. It doesn't represent the probability, but rather how likely this height is compared to other heights in the distribution. So it means how much is actually the likelihood. So this is now we are coming not actually defining the probability, but we are defining the likelihood of that thing. Now let's do it in Python, this calculation, then you will be understanding it very easily. And this is why the Gaussian probability curve is very important. We will be in order to calculate this one, we should bring this one as well. This is one of the new things that we have to bring here. We have to define the parameters. So mu, which is the mean, it is 170 now. We have to define that. Sigma, which is the standard deviation, is 10. You have to define that. And now we want to find the x, which is 180 centimeters. This is the x. And now we want what? We want to know the PDF value. So this is called PDF value. This PDF value, what will be the PDF value? It will be equal to norm.pdf of what? Of x, and log will be mu, and scale will be sigma. Scale will be sigma. And just print PDF value. And I hope it will work. It didn't work. Yeah, it worked. It's 0.2419. So this is the PDF value. So in order to understand it properly, one more thing, let's do something else as well. Let's visualize the Gaussian distribution. So assume that we have x values, and this x value is actually the Lie space of we just want to generate something. Yeah, we have to want to generate something. For example, 140 to 200, and so just assume x values, and then y values will be actually the norm.pdf of x values log mu scale sigma. This is now visualization of the of these values. So plt dot plot. Let's plot something. Plot what? Plot x values. X values. Y values. And label will be Gaussian I think Gaussian has Gaussian PDF. Let's do that. Again, problem with the syntax. So this is the Gaussian distribution calls. Let's make it a bit more interesting. We can add a line called PLT three line. A vertical line, AX V line. For what? For X will be X. Color will be red. Just assume that it will be red. Line style will be just dashed lines. Label, again, label will be not working properly. This is the label one. Label will be if X equal to X. I think it will work. No, it didn't work. Because, and then string, because of this problem, actually, because of this label one. Just forget the label and at least this is the Gaussian distribution, and this is the guy with 180 centimeters height. What does it mean 170 centimeters height? Mean average of values. So this is the people. This is, for example, assume that you have thousands of numbers, for example. Yeah? Or, for example, from 140, the height to 200 height. The average of height is 170. This is how this Gaussian curve is working. And then you want to find the probability density of a specific person with a height of 180. So this is called now the understanding of the Gaussian PDF curve, probability density curves. So these are the probabilities. Right now, we just predicted the likelihood of a guy with this match. So this is like that. A specific person. This is the mean value. And this is the PDF probability density function value. Yeah? So this is actually not the prediction, the probability, but actually the likelihood of that things. So this is called Gaussian probability density function. This is one of the things which is playing sometimes key role whenever you are assessing. There's another thing also called Gaussian cumulative distribution function. That's totally different thing. Also a bit that's called CDF. So those are all these functions. Whenever you're talking about the linear regression and you're talking about the logistic regression, you have to have understanding of two things. One thing is actually the likelihood, and another thing is actually the probability. So this likelihood is actually the prediction value multiplied by actual value. So this is the formula that all the time that you will understand it. So how the logistic likelihood works and how the linear likelihood works. Different understanding of interpretation of the models. Recently, in logistic regression, we understand here, for example, that how the likelihood worked. Yeah. In linear regression, you're becoming working with numbers, but in logistic regression, you're working with values. Those values are actually the likelihood of some things, and those likelihoods are important. Then this is why we did a round off here, if you remember this one. So this curve is also called a Gaussian curve, but this is not density curve, PDF curve. This is called CDF curve, this cumulative density curve. So this is also a type of curve of Gaussian curve. See, these are the likelihoods. These are the numbers that we worked with. So this is how you have to understand it, and this is the curve that we defined yesterday. That this is the curve, different curves. And this is the probability, and this is the odds ratio. See, this is the probability, or actually the likelihood. This was also the odds ratio curve that we defined yesterday. So these are how you will understand the curves of Gaussian curves whenever you are working with different logistic functions, and this is called the logistic distribution. Logistic distribution is like that. So what is actually the meaning of this logistic distribution? Look at this. Assume that this is 0, yeah, and this is to +1, and this is -1. So this is how you will be assuming. So this 0, this mean, is actually the highest point. This is the density function on the highest point. So toward that side, that will be the positive. Toward the right side, toward the left side, that will be the negative values. The understanding of that. And then we have another Gaussian cumulative distribution, and that's not probability distribution, but cumulative distribution. It's almost not this type of curve that we see. It's a bit different curve that we saw in our actual example, and we will be coming to that. Now let's understand that what's the cumulative distribution function. This is called the CDF, and this is the formula for the CDF. Normal distribution with mean mu and standard deviation sigma. CDF is given by, for example, this is now a totally new formula, different than the other, where the x is actually the value that to which we want to calculate the cumulative probability for that. The mu is actually the mean of the distribution, and the sigma is the standard deviation of the distribution, and ERF Z is the error function. So this ERF is actually the of function, that's the Z, the error function. The characteristics of CDF is actually the range of the CDF. CDF will be having a range of 0 to 1, and different types of limits. The same scenario, we can use the same scenario in height. Again, we will be assuming this person. Please mute someone who is okay. We will be using the Python for this function as well. assume that we have average of people. They have, for example, 170 centimeters of height. Yeah. And sigma, the standard deviation from that population, is actually 10 centimeters. Same example that we had previously. We want to know this CDF function for a person with a height of 80 centimeters. Now, how you calculate the CDF value? CDF value is actually norm dot CDF of what? Of X, this person height, of mu, and scale of sigma. Now, CDF. This is 0.84. Now, what does it mean? 0.84 means that if there's a bunch of people where the average height is 170 centimeters and the sigma standard deviation is 10 centimeters. If you're just choosing randomly one person within this whole population, 84% is chance there that the height of that person is less than 180. You got it? The understanding between the CDF, between the PDF. So this is how the CDF function value works. This is also Gaussian distribution value. And let's generate some again, the same values that we had generated previously. For example, X and Y, some we generated previously, plot another value. Now let's plot this Gaussian value with also with the whole thing that we have previously did. So this thing that we have done here, this thing that we have done here. So just plot the whole thing again. X value, it's the whole thing is the same thing. Let's just plot it and see. And this is now the Gaussian CDF cumulative density. I hope that you will remember that this is actually the thing. You see what does it mean? Px is lower than or equal to x. So this 84% is chance that the chosen person that you have choose from this whole population will be either less than 180 or equal to at least at the highest will be equal to the 110t, and 84% chance that it's less than 180 centimeter the height. So this is how the this is the cumulative probability. See, the whole thing is calculated together, and this is cumulative probability. So 84% is the chance that within this these values with this sigma of 10, for example, a standard deviation of 10 centimeters. So that this much will be this specific function. This is called CDF, cumulative function, and also we can have inverse cumulative functions for this one, but we will not discuss that. Now, instead of the Gaussian probability density function, which we had there, and that Gaussian is actually for the this is for the linear regression, yeah. But the same thing, we have a probability density function, but we can use it for the logistic regression as well. And we want to know the logistic regression there and how this logistic PD formula works. So in order to give you understanding of how the logistic PD formula works, I will give you the formula for the logistic PD formula, and you will see that. So this is the probability density function, but not Gaussian, but this is logistic. What is actually the x? X is the random variable here. Mu is the mean location parameter, which centers the distribution. So it means the mean value of that distribution. S is the scale parameter. It is controlling the spread of the distribution. So how the distribution is spread. And Euler value is the base of the natural logarithm, which is 2.7, and that's it. Logistic distribution, actually, the shape of this logistic distribution is very important. It's called bell-shaped. It's like the Gaussian distribution, but with heavier tails. It means more extreme values. So they are symmetric, and the spread is very controlled by scale parameter S. So the spread is very much important here. This spread is playing a key role here. So these are having larger ones. These extreme values are larger ones, and this spread is actually controlled by S. So this is the difference between the Gaussian and between the logistic regression. And its applicability that if you want to model the data with faster transitions between states, for example, logistic regression for binary classification tasks. And whenever you're doing that, so this is how this is how you can use that. We will be working with one final example on logistic distribution, and I think this thing would be completed the regression models. Let's assume that we are studying reaction times in seconds of people responding to a stimulus, such as pressing a button when a light flashes. So this reaction times, this example of reaction times. So just assume that we have an example of reaction times. Reaction times. This is very important example, and I think you will like it. So this is when a light flashes, for example, or just if you're driving, there's traffic light is just automatically become red, or automatically become from red. You're waiting, and you just saw it that it become green. So this reaction time, and you want to study this reaction time in seconds. You have, for example, mean reaction time, assuming that it's 1 second, and you have scale parameter reflecting variability in different reaction points. So scale variability is here. Actually, it's not the mean distribution here. It is 1 second, and the scale parameter, which is S, is actually 0.2 seconds. So now assume that this is like this. So you have mean reaction time, which is 1 second, and the scale parameter is 0.2 seconds. It means reflecting variability in reaction times. So it reflects variabilities, and one person had a reflection of 1.2 seconds, another 1.1, another. So different types of, but on average, this variability is 0.2, the reaction points. If you calculate the PDF for reaction times, so for this stimulation, so just assume, for example, in Python, that we have from SciPy previously, we just have norm, inserting norm. Right now, we will be importing logistic this time. And then we will be studying the mu. Mu will be 1, and scale will be 0.2. And then x values, just assume that we have an x value, generated an x value, for example, an array of something between different values. Now let's calculate this PDF value, this logistic PDF value. So this PDF value, logistic one, will be the logistic PDF value. Yes, the logistic PDF value. X values, log will be location will be mu, and a scale will be scale. So location will be mu, and scale will be scale, which is 0.2. So this is the PDF value, and what is actually this PDF value means? How much will be? So this is an array of these different reaction PDF values. So this is a huge matrix right now. Let's visualize this, and you will see how it will work. So just visualize that. Okay, we want to plot it. This one. Plot the reaction time, x values, PDF values. The label will be just the reaction values. So PDF value is, it will be, I think, PDF, not values, but value. PDF value. So this is now the curve, same curve. So 1 second is the mean value, and these are the extreme values. So 0 and 2 are the maximum extreme values. And so this is actually determining the common reaction time. So this is the standard ones. This is the scale. Scale is actually, it says to you, see 0.2 second. This was the scale. So these were the 0.2, actually the scale of this PDF logistic regression. It shows to you that this is the parameter on which it measures the spread of the curve. And from these logistic PDFs are often used for response times, for population growth, for physical systems. So these are the real-world application of this PDF, logistic PDFs are there. We also should keep in mind outliers. Sometimes maybe we have some outliers there, but we have to keep in mind that one as well. So this is a very basic understanding of the logistic PDF function. Tails are very important. They are called tails. These ones are very important here in PDF values, because if they have heavier tails, which means it assigns higher probability to extreme values. So that's one of the things, which is the difference between the Gaussian distribution. In the central peak, the peak is all the time in the mean, which is here, for example, 1 in around the mean. So this is how logistic PDF function works. The spread of it works, and how it will look like. These are the different types of distributions. linear distributions, logistic distributions, PDF and CD functions within these models. I think we covered almost everything from the regression side and the basics of modeling as well. And I understand that maybe there are some difficulties understanding the linear regression and logistic regression and all these calculations and all these formulas, remembering all these formulas. But please, my suggestion would be don't remember these formulas all the time. Just follow the main rule there. And whenever you're having the main rule, you will be facing some problems, but please don't be bothered based on those problems. You will find a way there, so you can solve it, but you have to understand the rule. The rule is very simple. We have linear regression models and we have logistic regression. If we have one numeric value and want to and have another explanatory value based on which we want to predict the numeric value, that's called linear regression. And we may have several explanatory values, maybe 1, maybe 2, maybe 3. So whatever we are having, we just demonstrated that you can just put 1 or 1 plus 1, 1 plus 2. So different explanatory value. So it's called linear regression and multiple linear regression. So based on different explanatory values, you can predict one response value or target value. But if our target value is a categorical variable, which is actually 0, 1, which was the category, yes, no, it's a Boolean type of response category, binary, which is called, they are calling it binary, then you have to use the logistic regression. There is just a different function. Instead of Euler's, you can just call logit function, and that's it. Still, you will be having one target variable that we are calling it response variable. And you can have different explanatory variables, maybe 1, maybe 2, and that's it. This is how it will work. So then these distributions and these functions are working properly but you have to understand it. One more thing that you have to memorize from this, that's how you will measure the accuracy of those models. Sensitivity, accuracy, confusion matrix, these are very important topics, and you have to all the time keep it in mind and proceed with. Whenever someone is asking for you to develop something, analyze something, before going to development and analyzing, you have to understand the concept of it. And based on the concept, you have to select a proper model to proceed with. If you're not selecting a proper model at the beginning to proceed with, then the result will be just nonsense. You saw just recently, yeah? There was a logistic regression model required for 0 and 1, and yesterday we applied just a linear regression on it. A total different outcomes, total different results from that model. Okay, thank you very much for your attention and participation, and our today's lesson is concluded, so we will be in touch within the week as well. If any assignments, I will inform you. I hope you all selected your own data sets, because starting from next week I think will be our last session. We will be discussing the modeling, so basics of machine learning. So I will be just touching some basics of machine learning, but after the next week, we will be working with the data sets, and you have to produce some actual things. So there will be no lectures, but I will be all the time available for you to provide you with the guidance. Then whenever your projects are completed, your profiles are updated, and everything is uploaded, you post all the assignments, then we can proceed with the certification. So my suggestion would be that please select your model. I don't want to give you everyone one task. I want to have different tasks for at least different people, because I just don't want that you all will have one project uploaded on your profiles. So I want everyone will have uploaded different projects. So that's it. Starting from next week, I will be launching a competition on Kaggle, and you all should participate there because it increases your online presence. So whenever someone is searching your name from the data point of view, so your name will be appearing because you have participated in a Kaggle competition. So please, and then we will be focusing on how to build your online profile and all those things. But my main thing is actually you have to understand what you're doing. And at the end, because it was very difficult for me that if someone asks you a very simple question and you will not be in the position to answer it while you will be having a certificate of advanced data analyst. And then another thing will be just a huge shame for myself as well that if someone asks you who was the instructor actually. So this is just the concluding topics for today. Thank you for the participation and our session is concluded. درس ما خلاص شد. تشکر از شما. If you have any questions, سوال اگه دارین, please ask me.
Have a good time.